Welcome back. Today, we're doing something really cool. We're going to trace a digital signal through a brand new biomechanical matrix of artificial intelligence. In this explainer, we're looking at what actually happens when we stop trying to just build a bigger computer and start trying to build a better brain. We're diving into the absolute cutting edge here, merging diagnostic routing with tri-frequency cognitive frameworks. Now, I know that sounds like a mouthful, but stick with me. As we unpack these concepts, you're going to see just how beautifully organic this whole thing really is. Okay, let's dive right into this. The big bottleneck in our current chase for artificial general intelligence is what researchers are calling a singular computational meat grinder. Think about it. Massive models like LLMs just force every single piece of data through the exact same rigid pathways. But biology? Biology takes a wildly different approach. A mammalian brain immediately characterizes raw stimuli and dynamically routes that info to highly specialized processing areas way before it ever tries to understand it. It's basically the difference between clunky, brute force scaling and sleek, organic efficiency. Think of this next part as our system boot up directory. First, we'll look at the AI meat grinder problem. Then we'll move through 4 cybernetic stages: sensory reflexes, dynamic routing, USDF partitioning, and finally, tri-frequency cognition. Then we'll wrap up with what lies beyond brute force scaling. Section 1. The AI meat grinder. The problem with uniform architectures. So the huge bottleneck plaguing traditional AI right now is the classic cold start problem. When an AI gets hit with unlabeled data, a uniform architecture simply doesn't know what to look for. Why? Because it just applies a single, generalized learning objective to literally everything. But as the research points out, and this is a great quote, biological intelligence does not push all data through a singular computational meat grinder. You see, biology respects the physical reality of different sensory inputs. It doesn't just jam a single perception strategy onto everything it sees or hears. To fix this meat grinder issue, researchers are proposing a unified end-to-end framework. We're actually going to follow a single unlabeled data trace across 4 really precise steps: sensory input, strategy routing, representation partitioning, and cognitive processing. We'll basically snap these biological puzzle pieces together and watch how they form a complete functioning cognitive loop. Section 2. Stage 1. Sensory reflexes, also known as the AI retina. You can really think of this first stage as the AI's retina. When a signal hits the system, it acts exactly like a reflex arc. You know, like pulling your hand away from a hot stove milliseconds before your conscious brain even realizes it's hot. Instead of doing any deep, heavy processing, the system just calculates 4 computationally cheap fingerprint features. Spectrokurtosis measures how peaked the frequency is. Dominant peak count identifies harmonic structures. Envelope peak to RMS ratio spots sharp, isolated transients, like a sudden loud click. And envelope kurtosis looks at whether the whole signal is smooth or abrupt. This entire process takes mere milliseconds. The system isn't trying to understand the data yet at all. It's just characterizing the raw physics of the signal, mimicking a pure biological reflex. Section 3. Stage 2. Dynamic routing, or objective selection. Now, what's really interesting about this next step is that with the raw reflex data captured, the system actually has to make a choice. The router uses those exact fingerprints we just talked about to dynamically divert the signal to one of 5 perfect learning recipes. So if the signal is highly structured and periodic, it might get sent to the spectral-weighted reconstruction recipe. But if it's super complex and multi-model, it might get routed to the mixture of Gaussians or MOG recipe. The architecture is dynamically adapting to the physical reality of the incoming data rather than stubbornly forcing the data to adapt to the architecture. And here is the mic drop metric: 95%. By running this diagnostic router on completely unlabeled data, the system manages to recover 95% of the performance you'd normally only get if you had manually, painstakingly tuned the model with perfectly labeled data. It hits this massive efficiency without ever seeing a single label. Just wild. Section 4. Stage 3. USDF partitioning, taking us into the latent space. Okay, so our routed data now needs to be processed and structurally partitioned into an organic database, or latent space. The tech running the show here is called the Universal Signal Decomposition Framework, or USDF. Picture USDF as a highly organized, totally futuristic dossier file. Where standard AI creates this tangled, monolithic mess of data, USDF steps in and enforces strict structural partitioning. It basically acts as the vital translation bridge between the raw spatial or temporal physics and continuous biological cognition. So USDF disentangles all that data into 5 distinct frequency-banded regions. But the real magic? That happens in regions 2 and 4, the overlap regions. These are not just hard boundaries, they're actually shared representational spaces. And this directly mirrors biological evidence showing how cortical oscillations in our own brains are frequency coupled. They literally share information right at the boundaries. Moving to Section 5. Stage 4. Tri-frequency cognition. This is the cognitive layer. Right, here's where things get really incredible. The partition data pulls bidirectionally into a hierarchical, mammalian-inspired cognitive model. This is called FGSGR, or Frequency-Governed Self-Graph Reasoning. Try to frame this in your mind as the absolute highest level of our cybernetic architecture. This is where the actual multi-scale reasoning happens. It organizes intelligence across 3 frequency tiers, behaving exactly like human brainwaves. If we break down this hierarchy, the ultra-fast gamma tier is operating in mere milliseconds, handling rapid reactive feature binding. Then you have the alpha/beta tier, which acts as this integrative middle ground, managing working memory over a span of seconds. Finally, the slow theta tier absorbs the most stable data for deep deliberative thought, top-down planning, and long-term episodic memory. It's a beautiful loop. The fast bands feed the slow bands, and the slow bands turn around and modulate the fast bands. So, the crucial point here is how this whole symphony is actually managed. The research shows that achieving optimal coordination across these 3 cognitive tiers requires exactly 2 minimal metanodes, which is represented as m equals 2. And guess what? Adding more governance capacity doesn't help at all. Actually, scratch that. It proves that massive scaling isn't always the answer. The brain relies on highly functional specialization with very minimal oversight. Definitely not some massive monolithic central processor. Section 6. Beyond brute force scaling. Let's conclude. Let's move forward and see how this all builds together. What does this fully merged framework actually mean for the future of AI? Well, if we trace this cybernetic data journey from start to finish across time, it looks like this. In just one single millisecond, the sensory reflex arc extracts the physics. Within 10 to 33 milliseconds, the gamma tier reacts. Over the next 10 seconds, the alpha/beta tier integrates working memory. And over minutes to hours, the theta tier engages in complex, top-down planning. We are literally watching data travel through temporal scales exactly like a thought moving through a biological brain. And this brilliantly illustrates the core takeaway from the research. Quote, "This merged system perceives the physics of its environment reflexively, routes data dynamically, and reasons across multiple temporal scales hierarchically. It's absolutely crucial to realize that this is a computationally efficient, totally biologically plausible path toward true artificial reasoning. It's stepping entirely away from the brute force scaling laws that completely dominate AI right now." I'm going to leave you with this final, somewhat provocative thought. Does the true path to artificial general intelligence lie not in building bigger, vastly more power-hungry data centers, but in looking closer at the elegant, highly specialized biology right inside our own heads?